Ladies and gentlemen, let's continue with chapter 9. We are following the textbook of Cengel and Ghajar. We are busy with natural convection, and we have already looked at 9.1, the physical mechanism of natural convection, 9.2, the equation of motion and the Grashof number, then natural convection over surfaces, different types of surfaces. There's a flat plate, a different configurations, horizontal tube, etc. And then paragraph 9.4, natural convection from thin surfaces, and 9.5, natural convection inside enclosures. So specifically paragraphs 9.4 and 9.5, we are not going to work through every one of those configurations. All of them are similar in the sense that the Nusselt number is a function of Reynolds, Prandtl, Grashof, and so far the Reynolds number doesn't play a role, and you will have to determine that and get the equations, and the fine print is very, very important. So you can just look at some of the examples in the textbook and some previous examples, and also the examples at the end of the chapter. You have to work out quite a few of them so that you can get a very good understanding and feeling of how to do it. It is not going to help you to take note and say, well, in the exam I will sort it out. That would not be a good idea. So what I would like to do in terms of specifically an example that is a good example of the natural convection from a surface but also inside an enclosure is to do an example of a solar collector. Okay. Now this example is based on the example in the textbook, however it is going to be different. So there's an example in the textbook on a solar collector, and this solar collector has an aluminium tube. And in the aluminium tube, there's water flowing through it. And the aluminium tube diameter is 50 millimeters. Okay. And on the outside of this aluminium tube is a glass tube, like that. There's the glass tube. And the glass tube diameter is 100 millimeters. Only one diameter of each are given, and I think for that reason we can assume that the thicknesses are very, very small. So the thicknesses are not that important. Okay. Now, what is given in the textbook in the example is that the net convection to the water is equal to 40 watts, up to 30 watts, but that is not maybe a good example for a climate like we have here in South Africa, so I'm going to use 40 watts. And this is 40 watts per meter. So for every 1 meter in length, the heat transfer rate to the water will be 40 watts. Solar collector being used for the heating of hot water for domestic purposes typically. So 50 millimeter tube, the water flows in here. Here's a glass tube, and in between there's just air. Okay. So it is just filled with air. There. So there's the air in the annulus. And we would like to make use of the radiation of the sun to heat the water. Now in this specific case, the water is going to stop flowing. So it stops, maybe the pump stops or something. And we are going to call this temperature on the outside tube T2, and that temperature we're going to call T1. Temperatures are T2 and T1, and the ambient temperature is 20 degrees Celsius. And what we are asked is to determine the two temperatures on the wall, T2 and T1. Now, if you look at this problem and you think of, for example, the natural convection that we've done so far, you would say, well, all right, if I think of the glass tube on the outside, so this is now the glass, then we have seen previously that there's convection heat transfer from the surface, because this surface is going to be at a higher temperature than that of the ambient. Okay. Then you would also say, but we also know there must be radiation heat transfer, because this surface is going to be heated. It's going to be warmer than that of the environment, and that is correct. And then you would also say, but wait a minute, this is glass, so we are going to have the radiation heat transfer from the sun going through there. And we've got this combinations of heat transfer going through the glass. Am I right? That is what you would say. Okay. But at the same time, then you would start looking at this problem, and then you would think, but wait a minute, now I've got another tube here, which is now the aluminium tube. And this aluminium tube is going to reflect some of the radiation. And this one is also going to reflect some of the radiation that is coming in. And now this problem starts looking as if it's a little bit complicated. You agree? Okay. However, if you take a good look at it and you relax a little bit, you will realize that, wait a minute, yes, some of the radiation is coming through, but the net heat transfer to the water is 40 watts that is coming in. Okay? And what is coming in must also go out. And it's not going out through the water because the water stopped. Okay? So therefore it means that if we look at the glass, then the total heat transfer rate from convection, okay, from the glass is going to be also 40 watts. Okay. Otherwise, the heat transfer is just going to increase and increase, and the temperature is going to increase. Because it's important that this is at steady state. So 40 watts is going in, the water normally runs, now you stop the water. Okay. And now we would like to see what happens with the temperatures on these two surfaces. What is coming in must go out. 40 watts goes to the water, okay. At the end, the net radiation. So that net radiation would be the total radiation which is going to be rejected to the environment. Yes, surely there is going to be a little bit of radiation, but remember that with these types of solar tubes, these materials are specifically selected so that the reflection in terms of the radiation coming in and what is being reflected is negligible. And this is what makes this problem a little bit different. It would be difficult for you to follow at this stage because you haven't done chapters 13 and 14, but you're going to do it later on. So this emissivity, where previously the emissivity was approximately 1, the emissivity would be now approximately almost 0. Okay. So don't try to make it too complicated. It is actually a very simple problem. We've got the glass on the outside and the convection heat transfer is 40 watts. Now we're going to calculate that temperature there, and once we've done that, we're going to look at the inner part, and I will get to that just now. So, now the thing is, if we think of the graphs of numbers and everything that we should calculate, we know that the properties are important. Okay, now the properties that we're going to have here for the natural convection is that of air. So we need the properties of air at a temperature. So the question is now, well, we don't have that temperature. Okay. That is the environment temperature, which is 20, and that is the temperature T2. So we have to go and get a film temperature. So let's start by making an assumption. And the assumption that I'm going to make is to say, well, let me select that the glass temperature is 40 degrees Celsius on the outside. Glass temperature, 40 degrees Celsius. If that is the case, then the film temperature must be equal to T2 plus T environment divided by 2. It's 40 plus 20, 60 divided by 2, that is a temperature at 30 degrees Celsius. Because this can be so confusing, and when I prepared for this, there were a few times that I've made some mistakes. So to be consistent, let's call that 2. To indicate the film temperature at surface 2, the outside surface. So the outside surface of the glass is 2, and the inside surface of the aluminium is 1. Okay, so that is the property TF2, and once we've got that, then we can go and calculate or determine the thermal conductivity, which is at that temperature equal to 0.02594 watts per meter Kelvin. The kinematic viscosity is equal to 1.636 multiplied by 10 to the minus 5 square meters per second. The Prandtl number is equal to 0.7267, and beta is equal to 1 divided by the film temperature, and that is equal to 1 divided by 303. Now, to make it clear, these properties, that it's going to be different than the properties at another surface that we're going to get to later on, I'm going to indicate this with 2's. Okay. So that's the thermal conductivity of the air on that surface, the Prandtl number, etc. Okay. So, if you now go and look at table 9.1, table 9.1, you will see that we need the Grashof number, or the Rayleigh number. So let's calculate it. So the Grashof number is equal to G B multiplied by T2 minus T infinite divided by the kinematic viscosity square. And again, to indicate that it is a Grashof number on surface 2, I'm going to use a 2 there, a beta 2, and a kinematic viscosity 2 there. So G is equal to 9.81, beta is equal to 1 divided by 303. The surface temperature, we don't know what it is, but I've selected 40 degrees, made the assumption of 40 minus 20, divided by the kinematic viscosity, which is equal to 1.636, multiplied by 10 to the minus 5, everything squared, and that gives me a Grashof number of 2.594 multiplied by 10 to the 6. The Rayleigh number is equal to the Grashof number multiplied by the Prandtl number. But it is the Rayleigh number at 2. So, for that reason, we need the Grashof 2 and we need the Prandtl at that location. If you go and multiply this now with the Prandtl number, there it is 0.7267, then the Rayleigh number is equal to 1.885 multiplied by 10 to the 6. Yep.
Should the Grashof one not be multiplied by the characteristic?
Should the?
Grashof number.
Ah, sorry, you're right, yes. The diameter, is it square, is that right? Or is it third? Third, yeah. Diameter third, right. Okay, thank you. Okay, so the diameter third is 0.1 to the third. There you go. Thank you. Okay. Okay, that is actually quite a very important dimension. It can be an L there. But how do I know if I should use the diameter or which diameter I should use or the length? You have to go and look at the formula, the information that has been given, and you'll see for a tube it is the outer diameter D that should be used as the characteristic length. So from table 9.1 we can get the Nusselt number equation that we have also used previously. It is equal to 0.6 plus 0.387 multiplied by the Rayleigh based on the diameter to the 6 divided by 1 plus 0.559 divided by the Prandtl, everything to the 9 divided by 16, and then all that closed in brackets to the power of 8 divided by 29, and then everything to the power 2, something like that. Okay. And again, very important, there you can see the Rayleigh number is based on the diameter for that equation. Okay, I'm not going to put in all the values there because it is quite boring. Everything is there. We've calculated the Rayleigh number, there it is. And we've got the Prandtl number, so that's actually the only two things that goes into that long formula. And if you go and do the substitution, you will see that the Nusselt number then works out as 17.45. Again, when you calculate something like that, always think about it. Does it make sense? Natural convection, yes. Up to 10, 20 values like that, but not normally thousands, not 10,000s. Also, it can't be smaller than 1. You should also, if you do that, then you must realize that you've made a mistake. So Nusselt number, the Nusselt number is equal to the heat transfer coefficient multiplied by the diameter divided by K, and that is equal to the Nusselt number. The heat transfer coefficient is what we want to calculate. The diameter is 0.1. The thermal conductivity is equal to 0.02594, is equal to the Nusselt number, which is 17.45. So from that we can calculate that the heat transfer coefficient is equal to 4.526 watts per square meter degree Celsius. Okay, are you all with me so far? Right. So what we now can do is we can say, well, the heat transfer rate must be equal to the heat transfer coefficient multiplied by the surface area multiplied by the outer surface of the glass, T2, minus the environment temperature. Okay, now, if you look at that, you'll see that we've got actually everything. We have the heat transfer rate, we've got the heat transfer coefficient, we've got that surface area, we just need to calculate it. The outlet temperature, T2, we have set is equal to 40, and that temperature we have. Okay. But what we want to do now is we can do one of two things. We can go and check that if our assumption is correct of a temperature of 40, that the heat transfer rate would be 40 watts. Or we can put in the 40 watts and we can go and calculate what the outside surface area then should be. Okay. And that's what I'm going to do. So I'm going to say, well, the heat transfer rate is 40. It's equal to the heat transfer coefficient, which is equal to 4.526, multiplied by the surface area, which is equal to pi, multiplied by the diameter, multiplied by a length of 1 meters. So the 40 watts that they've given us, remember, the net heat transfer rate would be 40 watts per meter. So that is my surface area multiplied by the heat transfer coefficient multiplied by T2 now minus 20. Okay. And this temperature, T2, like that, is now going to be my new temperature. I would like to calculate it and check if it is 40. Well, if you do the calculation, you'll see that it is going to be 48.69. Okay. So, estimate was out by about almost 9 degrees Celsius. Right, so what do we now? What do we do now? We need to iterate, because obviously all these properties were based on the assumption of 40 degrees Celsius. But our calculation shows it is almost 49 degrees Celsius. So you can now go back and you can put in this value, or you can put in a new selection of 45 or whatever. I used that one, and I used the program ease, which is very easy. You can just then change this value and it will change all the properties for you automatically, redo all the calculations, and I've iterated it, and I have found typically after the second iteration it goes to 46.04, and then after the fifth one it was 46.6 degrees Celsius. It's the wall temperature on the outside of the tube. Any questions? Okay, so this is now for the glass. The other part of the question was, we also need to get the wall temperature of the aluminium. So let's do that. So what we have now is that we've got an annulus, and is an enclosed annulus. So we've got that as the aluminium, and there is the glass. And this is now the area in which we have natural convection. And this is the previous paragraph in the textbook. It is about enclosed areas. We've just started looking at the case, for example, where we've got glass. And inside the glass, we've got a closed area. Here's an annulus, it's the same thing. And if you go and read there, again, it's very important, the small print, then there are a few equations that are given for cases like this. So for example, on page 553, the following very important information is given. It says that the transfer rate in the annulus would be equal to 2 pi multiplied by an effective thermal conductivity, divided by the ln of the diameter ratio. And that is equation 956 in your textbook. Then it would also give that K effective divided by K is equal to 0.386 multiplied by Prandtl divided by 0.861 plus Prandtl, everything multiplied by F cylinder, multiplied by Rayleigh L, everything to the quarter. And that is equation 957 in your textbook. Okay. So we can now immediately see that here's a K effective. Okay, there's a K effective that we can do. Now here's something new here, F cylinder. Okay. And F cylinder is also given in your textbook, and it is given as the linear ratio of the diameters to the fourth divided by LC to the third divided by the inner diameter to the minus 3 divided by 5 plus the outer diameter minus 3 divided by 5 and everything to the fifth. And that is equation 958 in your textbook. And again, now here's something new. Here's an LC now that you don't know what it is. There's no obvious equation, but if you go and read the text, it says that LC is equal to the outside diameter minus the inside diameter divided by 2. And again, if you go and read it now, it refers to the fact that if you now go and select or use the Prandtl numbers in here and the Rayleigh number, you have to go and do it at the average temperature between the two surfaces. So if that is the temperature T1 and that's the temperature T2, your film temperature must be based on the average of the two. Okay. So now that we know that, let's continue, and I'm going to continue by again selecting or assuming the temperature of the aluminium, because we don't have it. We have determined now that the glass temperature is going to be about 47. Okay, so what would you select here for the inside? I've selected 90. Do you think it is too high or too low? Okay, well, let's see. So if we assume a temperature of 90, then let's go and calculate the film temperature, T1 plus T2 divided by 2. And take note, I use a 1 now, because 1 is on this surface here. Or, sorry, not on this surface, but in this area here. It's not in that area there. Okay. So this is now equal to 90 plus the glass, which is 46.6 divided by 2, and that is 68.3 degrees Celsius. At that temperature, we can go and determine all the properties. Okay. K1 would be equal to 0.02613 watts per meter Kelvin. The viscosity 1 would be equal to 1.66 multiplied by 10 to the minus 5 square meters per second. Prandtl 1 would be equal to 0.7181. Beta 1 is equal to 1 divided by 273 plus 68.3. These are all the properties, and LC is equal to the outside diameter minus the inside diameter divided by 2. The outside diameter is 100 millimeters, the inner diameter is 50, divided by 2, and that is equal to 0.025 meters. Right. Now the Grashof number. So the Grashof number is equal to GB beta multiplied by T2 minus T1 multiplied by a characteristic length to the third divided by the kinematic viscosity. Okay. Previously, we have used here the diameter. Now it specifically says we have to use that characteristic length LC. Okay. So that is known. So that viscosity is at 1 and that beta is at 1. It is at the average of that temperature between the two surfaces. So if we now go and calculate the Grashof number, at 1, then it is equal to 9.81 multiplied by beta, which is equal to 1 divided by 273 plus 68.3. Multiplied by the temperature difference, 90 minus 46.6, multiplied by the characteristic length, which is equal to 0.025 to the third, divided by 1.66 multiplied by 10 to the minus 5, everything to the power of 2, and that gives us a Grashof number of 48,532. Yep.
So is it T2 minus T1? T1 minus T2.
It would be the temperature difference between these two, yeah, T1 minus 2T2, T2 minus T1. So you won't have a negative Grashof number. You'll always just fix them quickly. Okay. Okay, so yes, we can change this to T1 minus T2. And the Rayleigh number, the Rayleigh 1 would be equal to Grashof 1 multiplied by Prandtl 1. Here's the Prandtl number, so we just need to multiply that by 0.7181, and that would be equal to 34,851. You all with me? So quiet? Okay. Then we need to calculate F cylinder, and that is equal to the ln of the diameter ratio to the fourth divided by LC to the third D1 to the minus 3 divided by 5 plus D2 to the minus 3 divided by the 5, everything to the fifth. Okay, this just needs to be calculated. That ratio is 2, so it's the ln of 2. Put in all those values, and the result is a value of 0.1466. Okay. Now, K effective. K effective is equal to 0.386 multiplied by K multiplied by Prandtl divided by 0.861 plus Prandtl, everything to the quarter, multiplied by F cylinder, multiplied by Rayleigh L, everything to the quarter. Okay. So take note, if I just go back to this equation previously, here it is. So I've just multiplied by K to get K effective. Okay. K effective is equal to 0.386 K, so previously the K was here, I've multiplied it out. Again, I don't want to waste your time, so the K, of course, would be K at 1. The latest values, Prandtl would be at 1. Prandtl would be at 1. The Rayleigh would obviously be, there is this Rayleigh that we've just calculated, Rayleigh 1. So let's just change this to Rayleigh 1 like that. Okay. So plug it in, and you will get an effective thermal conductivity of 0.07699 watts per meter Kelvin. What is this effective thermal conductivity? It is a sort of a heat transfer coefficient, that takes into consideration the convection heat transfer and the conduction and puts everything together in one term. So that is all it does, in principle. So now we can calculate the heat transfer rate, which is then equal to 2 times pi multiplied by K effective divided by the lim of the outer diameter divided by the inner diameter multiplied by T1 minus T2. So again, what you now can go and do is you can, with your assumption, or my assumption of 90 degrees, you can go and calculate the heat transfer rate and see if it is 40. If not, you can change this value. Or what I did is I've used 40 there and calculated the wall temperature. So the heat transfer rate is equal to 40. It's equal to 2 times pi multiplied by K effective. And K effective is equal to 0.0769 divided by the lim of 2, because it's 100 millimeters divided by 50 millimeters, gives you the lim of 2, multiplied by T1 minus the environment temperature, which is 20. Sorry, not 20. 46.6. It's a temperature difference between the two tubes. It doesn't have anything to do with ambient. Okay, so now we can calculate the wall temperature of the aluminium, and I've calculated 103.9 degrees Celsius. Okay. That doesn't mean it is correct, because this is based on my assumption of 90 degrees. So what I did is I've used that value. I did go back in terms of my assumption, put it in here, recalculated TF1, and went through the whole problem again. And then I've got a value of 100.4 degrees Celsius, and it quickly converged to, I think about after the third one, to 101 degrees Celsius. So if that water is not under pressure, it's going to boil. Does that make sense? No questions? Nothing? Okay. Thank you, ladies and gentlemen. That's the end of the class. Yep. So.